Snowgrove from Newcastle, and we decided we should try to record neonatal retinas on this. And so we had this hard drive full of data, and then we had no idea how to analyze it because there wasn't anything at the time available. So a lot has changed in a short span of time. So since then, that technology has gone into an in vivo system that we're going to hear about now. So thanks for coming, Luca.
Thank you so much.
So,
okay. I will find out. Can you hear me? Yes. Okay. So it's really a great pleasure to be here in Edinburgh. Thank you so much, Matthias and Alessio, Nina, for inviting me and to have the chance to introduce you about SiNAPS. I will go through the technology, trying to explain you what are the rationale behind this technology, how we realize these devices, and then also to show you where we are with some of the experimental studies we are doing and where we are going actually with this technology. I will also give you an introduction on the history of what we have been doing over the years. And this, I think, is important because in the previous work done also, as Matthias highlighted in vitro, ex vivo, retina, we learned a lot about how to sample neural activity. And many of these concepts are now actually still important for progressing active dense probes. So just a conflict of interest statement, I think it's important. I'm co-founder of 3Brain, but I'm not part anymore of the company. And I'm co-founder of Corticale. I'm shareholder, but I'm acting only as scientific advisor, and I don't have any active role in the company. So I'm PI at IIT. And actually, my lab is a small unit. So this is where SiNAPS come from, just a pool of very bright scientists and colleagues with very heterogeneous expertise going from engineering, from computational developments, experimental neuroscience. And the rationale of the lab is really to merge these expertises together because I think it's really at the boundary of these fields where you can create innovation. So this is located in Genova, and IIT is actually spread all over Italy. You are more than welcome to join us to visit us anytime. So I will, as I said, go through a little bit of history, how we shifted from passive to active devices, talk about active pixel sensor, which is actually the core concept of SiNAPS and also of our previous technology. And then I will go a little bit more into SiNAPS technology, probes, different types of devices that were built, and what's next. Some example of what's going on in the lab right now. I'm here also with Matteo Vincenzi, who is taking care of the signal processing and the computational development in the lab. So he will stay the full week. Please go back to him if you have any questions. So from passive to active, I think it's, for this audience, quite obvious. The challenge is really try to get as sparse as possible sampling all over the brain, so brain-wide recording, while keeping spatial temporal resolution to access single neurons. And how to reach that crossroad is still the challenge. Okay, still nowadays we don't have the right technology for that, I think. So it's still margin. There is still margin for further developing technology. So we need innovation to get single neurons over very large areas in the brain. And so where are we now? We know we heard before we are at the scale of hundreds of single neurons that are detected in single specific circuit spread across multiple circuits. But this famous plot is actually on the way to go further and keep going on in number of units. And the technology that brought us there are coming from the old school microwire that are widely used nowadays to microstructure devices. And I will go briefly through that. So, of course, CMOS technologies like NeoPixel, NeuroSeeker development carried out in Freiburg, and what we have been doing in SiNAPS are kind of bringing the number of single neurons within sample up. So microwires are kind of well-known technologies, very stable in vivo, and we'll come back to this later in the last part of my talk. And you know, Paradynamics is actually working in integrating more and more wires connected to CMOS circuitry to sample in a sparse way in the brain. And we also know that passive silicon probes were introduced in the 70s, Utah and Michigan probes, and these enable to actually provide the community different tools for recording from multiple species and also humans. And in 2000, a big emphasis on flexible polymeric probe, and the major reason of that is actually to have very conformable probes that can have properties of the device itself that somehow matches better the mechanical property, the biomechanical property of the tissue, and this to improve stability. And but with this technology that we classify as passive, for each wire we need a front-end amplifier. So basically, if you scale up the number of electrode size, you end up with a very bulky instrumentation outside. To overcome this issue, actually, what has been done in the field was to bring in CMOS technology, and Intan is actually the chipset that is used in many systems that allows to record in a very small form factor device, and also deliver electrical stimuli. And I'm citing here Neuralink because I think this is an example of a hybrid technology where we combine integrated ICs, CMOS, and flexible devices to sample from the brain. This is, as you know, everybody's talking about Neuralink right now. But I think that the interesting part of what they've been doing is within the insertion technology. So this robotic system that allows to precisely locate electrode sites in the brain in an automated way. So starting 2000, we started developing CMOS-based devices. These were developed mainly for first in vitro, ex vivo recording, and we started with the active pixel sensor concept around 2001, first publication. The work of Andreas Hierlemann's lab has also pioneered the field, going very dense in the electrode array itself and showing how this density allows actually to sample neuritic propagation in culture systems. And we know in 2017, there were publications from the NeuroSeeker project, NeuroPixel probes, and us on SiNAPS that somehow introduced into the field these technologies. Corticale is our startup company that is realizing these devices in volume and was incorporated in 2021 to make these devices available. So let me summarize. We can distinguish between passive microelectrode arrays. In that case, each electrode site is wired individually on the probe to an external front end. We can distinguish hybrid microelectrode arrays where the CMOS circuitry is embedded in the device itself. This is the work of Kendall White's lab, very well known because it was one of the first integrating that for implantable probes. But still, you are limited in how to route actually these electrodes to the external world because you have still a connectivity issue. And the active microelectrode arrays have somehow solved this issue because we are not constantly sampling, connecting each electrode site to the external world, but we are sampling from one of them after the other one, like what we do, or we are selecting a sub-array from the available number of electrode sites as in NeuroPixel devices. So using CMOS technology together with microtechnology allow to scale up the number of electrodes as well as the density of electrode sites. So let me spend a few words about the active pixel sensor concept because this is something that is at the core of what we have been developing and is somehow distinguishing SiNAPS in respect to other active lens probes. So the active pixel sensor concept was developed for CMOS light imager. So basically the idea was to have a pixel that was in the 90s where you have a photosensitive element and a circuit just below that is actually enabling to sample photons, right? So what we did in our work was to take this concept and instead of having a photosensitive element in the pixel to have an electrode and a front-end amplifier just underneath each electrode site. And of course, this is challenging because of the size of the circuit. We're talking about a few tens of microns per pixel size and the integration and fabrication issues. So we started in vitro, and the other concept we basically introduced over time was really to go into heat maps to represent electrical activity, because having thousands of channels, it was becoming very hard to just follow single traces, right? So that's related to bioelectrochemical sensors, and that was one of the first development of this active lens technology. So with these devices, these were 4,096 electrocytes, closed in space by 20 microns. We have been working a lot on culture systems, neuronal systems, brain slices, retina, just to give you a flavor. This is on culture data. You see these typical busting events that appear in the neuronal culture. This is actually on a brain slice. And you see activations in the pillars that you see the positive, negative field that propagate into the cortical area. And also here you appreciate the imaging capability of electrical activity, as was pointed out before. And let's move this, sorry. In the retina, as Matthias said, this is kind of retinal ganglion cells recording from a very large area of explanted retina from the mind. And what we've been doing with Matthias, I just added this slide because I think it's a good remember of what we have been going through. We have been building up a system where we're able to control light projection, so projecting light over the expanded retina to look and investigate RGC responses and the circuit responses. And what has been built was also a pipeline, actually, that was at the beginning of the development of also a spike interface, I think, where we were collecting data from this 4,096 electrocyte. We had to sort. We had this work on cell reports on spike sorting, where we were exploiting spatial correlation to identify single units and locate them in space and discriminate units. And a video that I like a lot to show is this one on the distinction between on and off cells in the retina, where you see the on-off stimuli, and you see the on population responding to the stimuli while scanning the stimuli on the retina, and the off stimuli responding to the stimuli. So this is on the scale of 4,000 channels, and that was done in vitro. What about SiNAPS? SiNAPS is actually the major work of this guy, Gianni Colangozzi, a CMOS designer in the lab, and of course, it's a joint effort of the whole lab. And the core concept can be summarized here. I compare to NeuroPixel to distinguish the differences. I highly appreciate NeuroPixel work, but I just reassure the community. NeuroPixel devices actually integrate an active matrix on the shank and integrate the amplifier for low frequency signals and AP signals in the base of the probe. And so you have to select a subset of electrocyte you want to record from before initiating a recording. This is one way to get high density. What we have been developing is a concept where actually the front-end amplifier are integrated underneath each electrocyte. Because our rationale was, if we place electrodes in the brain, we want to record from all of them. And we want to record full bandwidth from almost DC level up to 5K bandwidth, just to give you numbers. So this was a big challenge and allow us to drop down the overall form factor of these devices and enable recording up to 1,024 channels as we have right now. So just some concept to go through this development. So when you talk about the electrode pixel itself, you have to, in CMOS circuit design, you have to find trade-offs between, we have a fluctuating DC offsets that we have to deal with. We have noise, we have silicon area, and power consumption. So if you decrease silicon area and you decrease power consumption, you basically increase noise and you get into trouble. So it's very tricky to find the right trade-off among these different elements. And to solve this scaling bottleneck that was reported in 2017, actually, this scaling bottleneck is due to the conventional circuits that are used in electrophysiology. This famous circuit from Harrison, where we are using an AC coupled solution. So we have a large input capacitor C1 here that is actually filtering the band. And if you want to integrate this capacitor in a small pixel of something like 20, 30, 40 by 40 micron in size, you are in trouble because the area of this circuit, of this component is too large. So to avoid this, what we have been developing is a circuit that uses an auto-zeroing. And basically what we are doing here, if I can show, yes. So at a certain time, we are sampling the DC level on this capacitor here that can be quite small. And then in operation, the circuit is actually subtracting this DC level at the input of the front end. So the system regularly recalibrates the working point of the amplifier to avoid to go into saturation. And with this concept, we were able to avoid large input capacitors and to realize the first pixel that was something like 26 by 26 microns in size with 46 dB gain and a cutoff frequency of 4K. And actually, it is a DC coupled solution. It's not anymore an AC coupled solution. Noise was 7.5 microvolt RMS over the full bandwidth, 0.3 to 7.5K. So this is one concept for the electrode pixel itself. What we wanted also to add was to realize modules that were dense in number of electrodes. So this was to provide high definition and high definition in space and time. And to do that, we have integrated on probe the so-called time division multiplexing circuit. Basically, a module of 32 electrodes is multiplexing time over a single output. So by scanning rapidly among these different electrode pixels, you can then stream out on one single output channel these 32 channels. This multiplexing allowed to basically achieve a 20K sample frequency per electrode sites, as well as to drop down a number of output wire of the device itself. And then at this stage, we have been integrating the ADCs and sampling circuits off chip. So we were not integrating that on chip, and that's the difference in respect to NeoPixel. These are these modules, and of course, it led to a dimension of, for this specific case, of 448 microns by 70 microns in silicon area, and it can also sample up to 25K per channel. And I'm highlighting this because this community knows really well, actually, different cluster of electrodes can sample multiple units, and that's why we need this spatial resolution. This is a view of the paper done with Matthias in 2017. That was done in vitro on the retina, where we were co-localizing and verifying that the unit was well relieved. So the other point was to build up a modular technology that could be scaled among different layouts. We know that the neuroscience community is actually needing different types of probes, longer one, shorter one, more electrode distributed in space, and so on. So this technology is very modular in the sense that we can basically copy and paste modules to realize different types of devices. And this is an overview of what has been done. Some of them, those that have been realized, these are also commercially available. Other probes that are in this table are not available. These are prototypes we are developing in the lab, and I will talk a little bit more about that later on in the talk. This goes from single shunt probes with 256 electrode sites to 4 or 8 shunt probes with 1024 channels. And these probes that have a very tiny base, these are for NHP recordings. And the idea of integrating this tiny base was to be able to combine that with cannula to go deeper into the brain. This is still an ongoing development. But the specification of the electrode site is basically an electrode site of 14 by 14 microns. It can be scaled down, of course, and a sampling frequency of 20K per channel while recording from the entire array. So if you compare form factors, this technology approach allows to, this is in scale actually, allows to really drop down the overall sizes of the devices. And this is something we are really exploiting to go in chronic settings because you avoid a lot of the connectivity outside of the brain area. And this is actually a recording that was done in Janilia, in Harry's lab, where we have been comparing, actually, we're trying to compare the performances between NeoPixel and SiNAPS data but actually you can appreciate that the signal quality is kind of similar in terms of SNR. The advantage of SiNAPS is that if you count the overall silicon area of the device and you count the number of channels you can actually stream out data from, the recording channel density is about 10 times higher compared to other devices. This also means a much higher volume of data that we have to deal with, and that's a challenge for this community, I think. And for us, of course. So we are at about 25 electrodes per channel per square millimeter. Just briefly about how they are realized. So this is actually what we do in my lab. So my lab is a research unit focused on realizing prototype, exploring new concepts. So we build up a prototyping process where we actually design CMOS circuit, we send out to microelectronic fabrication, we get them back, and in our clean room, we actually structure few samples at a time, and this allows to verify the functionality and perform first experiments. And this is an overview of the process. I'm not entering into the details, but actually we modify the electrode materials. We are using platinum electrode sites. We structure devices in different ways. I will show you the results of that. In Corticale, actually, this process has been scaled up to volume, and that was one of the major challenges for the company. And now these devices are realized at 8-inch wafer levels to ensure the volume production. And of course, here you have an overview. You see thousands of them on a single wafer. So the full process is already certified for medical devices, and that's another value of the company itself. Let's go back to the lab. This is actually the research platform we built up for performing our experiments, but also for our collaboration in various projects. And this is based on the SiNAPS systems. We built up a hardware, a base, which is FPGA based. And this is connected to a PC for data acquisition. We are using a camera link interface to avoid issues in data rate. And we designed completely the software interface for data acquisition and exporting the data. Just to give you some numbers, with 1024 channels, 12-bit resolution, 20K sample per second, we are at about 250 megabits per second, which is about 10 times higher than 4K Ultra HD monitors. And that's something that gives you the idea of the volume of data we have to deal with. And this is an overview of the system. You see it's a kind of small box that you can place in the system. You can also stream auxiliary data input to synchronize activity with behavioral systems. And this is the view of the setup actually for acute recording, but we are routinely working chronically also. And of course, we are using more and more spike sorting for analyzing this data. And kilo sort, but also we want to use spike interface more and more. So just a few highlights on data. This was realized with 412 recording probe in acute condition in mice, and you can sample continuously from cortical area, hippocampal area, and thalamus area, both field potential as well as single units activity. You see the raster plot on the sides, and the noise level at that time was 7.5 microvolt RMS. So this was a nice results. Here we shifted to multi-shunt probes, and also here we can sample continuously, but exploiting a lateral axis, so spanning the scale of the spatial scale of the resolution. And I want to highlight you this data. This is part of an ongoing paper we are preparing with Zach's lab and Sirota's lab. Here you see actually an 8-shank 1028 probe that was designed basically to cover almost the entire width of the hippocampus in the mouse. So we can actually sample both vertically and horizontally from an area of about 4 square millimeters in area. And the quality is pretty high. And this is actually used for analyzing and identifying also single units in the circuitry. And you can clearly see field oscillation and the units that were detected. Representing that data is another big challenge, and this is something interesting for this community. Oops, going back. So let me just highlight that this technology now through Corticale is made available to the community. NeuroNexus has a commercial system that is integrating that. Plexon also. And this is all. No, come on. I want to show you the video of this recording. This is from the Plexon systems where you can identify hippocampus in the mouse, and you see the road traces on the other side. This for Harvey, since he's here also. So this technology is available, but let me shift toward ongoing developments to show you what we are doing in terms of device development. And let me start with addressing the development of SiNAPS-probe for non-human primates. This is actually a work done with Newcastle University with Stuart Baker, and we call this probe Baker probe. It's a 1024 electropixel array. In that case, we added an additional layer of multiplexing with the DDR in order to sample from the entire array, and the 1024 channel here in that case have a noise level of 6.5 microvolt. Arrangement are on 4 columns to exploit the spatial density and resolve single units. And here you see we have also Vivian and Sandra in the audience that are taking care of these experiments. Here is the protocols they build up to localize where to insert. This is an acute condition. The monkey is performing behavior, and there are multiple recordings synchronized with this data. And this is actually referring to a specific point and entering specific orientation. This is an overview of non-curated data coming up from spike from kilosort. Of course, there are probably noise also inside, but you can see roughly the amount of data you can collect from these probes. And I think you can better appreciate that actually in this movie, where you see single units detected in specific. This is a selection of such channels. You see spikes and fields in the motor cortical area. Another development which is really exciting for us is to move this technology into chronic settings. And this is a big lab effort in terms of engineering to minimize the sizes of the connectors. In that case, you see a view of what we achieved in the previous generation. It's not the last one. And we are using a cable connection at the moment, and with a commutator on the top, so the mouse can behave in a cage and perform behavioral tasks. So this has been integrated, and this is an overview of data collected at day 0, just after implantation. And just after implantation, of course, because of the dimpling of the tissue, you lose first layers of cortical activity. If you wait something like 30 minutes, you can get out the full array working and recording units. But after 28 days, although it's still not optimized as a system, we got a pretty stable activity recording from the full probe. And this goes, we are in prefrontal area. And the reason of that, because it's the work of Christine focusing on social interaction and social behavior. And this is a better view of these recordings that were carried out at multiple sessions, day 0, day 6, day 13, 21, and 28. You can appreciate that after about 10 days, the probe gets more stable, and that's due to the tissue that is adapting, integrating the probe better. The ceiling is much higher, and you get even higher quality of recording. These probes are 256 channels, and we get about 200 something units continuously from all of them, all the probes. And this is a pretty good result. Consider that these devices are not using at the moment a flexible interconnect, so they are mounted on the skull, actually. So this should introduce more issues in terms of stability, but actually, because of the dimensions, it seems that it's working pretty well. In this direction toward chronic implants, one of the projects that was carried out by Joao, and there's an ongoing project right now, is the so-called Chromos probes. In that case, we want to exploit CMOS technology to downscale even more the device size. And as you know, just to highlight, one way to get highly stable recordings in vivo is to use polymeric threads and to insert them in the brain with this tungsten wire or supportive structure that can bring down the electrical sign in the brain. On the other side, we know from history, actually, that microwires get a very stable recording. The work of Nicolelis and others, Monkey, have been showing a very long stability of microwire recordings. So that's why we came up with the idea of realizing actually CMOS microwires. So since we have front ends that are about 30 by 30 microns, we might scale down to a few tenths of microns the width and thicknesses of these probes. And this is the hypothesis that drives this development. And this is a view of this device. It's a scanning electron micrograph. You see this device, it has 26 microns in width, and it's 15 microns in thickness. And it integrates at the moment 64 channels. That's for testing the technology over a length of 2.3 millimeter. So it's very, very tiny. We have been testing it in comparison with conventional probes that are about 80 microns in width, and looking also into the foreign body reaction through immunohistochemistry and observing the stability over time. But something I want to highlight is this work carried out by Alberto Ferner, PhD student in my lab, who is actually, he has been developing a setup to measure the insertion forces of this probe once approaching the surface of the brain. And this has been applied first in agar gel models to evaluate the performances of these probes, but also in vivo then. So if you are sensible to experimental videos, maybe just switch off the video or look at to another side. I will show you just some of these examples of implantations. And because I think it's interesting to see, this is done in a post-mortem condition. So you see the implantation, you see the device that is approaching, is dimpling the tissue, you see the force rising up, and then once penetrating, it goes into the tissue. And you see the force dropping down to very low value once you are in the tissue. And if you use a multi-channel probe, and this is in vivo, with the living animals, you see that the dimpling is actually larger because it's distributed all over the area. And you also see this micromotion overlaying on the force measurements. And that's another interesting parameter we are looking at. What I wanted to show, these are 80 microns and 100 microns in width respectively, over 30 microns in thickness. If you take one of these Chromos probes, you barely see them in this video, just see the reflections. Once you see the change in the reflections, but you see the force increasing and dropping down. And here we are about 200 micron Newton peak forces, so much lower compared to what we were observing before. And reducing this initial tissue damage is very important to stabilize the recording, and especially in chronic condition, because you reduce a lot the tissue response. These devices are also working well. So this is an example of recordings from these 64 channels implanted. This is an acute condition, and now we are routinely using them also in multi-probe configuration to sample activity chronically in mice. So I've been bringing you through a little bit of developments of what has been done in vitro, what we are doing now in implantable probe SiNAPs, but of course the lab is looking into new concepts, and something we are now working on is to actually fragment this array, this pixel array, in very tiny devices. I will cite the work done on neural dust, but this is the concept. So the idea initially for us was to realize these tiny devices to go in organoids or 3D constructs. But I will show you how we are moving now this concept into in vivo technology. So these were initial works done on this 100 by 100 micron size electrode single self-standing devices. And I like you this work because one of the findings we have been reporting is that by controlling the surface property of these devices, you can actually determine where the device ends up in these 3D constructs, being more internalized or external, just by changing the surface properties. You know, this is more technology-driven science. But of course, you know, the work done and presented concerning neural dust. This is actually a microsystems, and recently steam dust is another concept for delivering electrical stimulation using best cultural ultrasound communication. What we are actually targeting in a European Innovation Grant, Council grant is the development of a small neural dust-like device, which is called microbot, which is 100 by 100 microns, and in which we are providing recording sites as well as different modalities for modulating neural activity. And of course, we will select one of them. This goes from optical delivery. We have colleagues working at INL on micro LEDs for optical stimulation. We have colleagues working on nanomaterials for mechanical stimulation and other modalities, or ions delivery to modulate local reactivity, as well as electrical stimulation. And by the way, University of Glasgow, which is actually nearby, is also involved. And they are working on magnetoelectric antenna, which is a way to drive power and read out data from these devices. Of course, this is a young project. We are first year, but we already demonstrated our redesigned front-end circuit, which is about 30 microns for a multi-channel recording system we built up, connected to a neural nexus 32-channel probes, and highlighting good signal-to-noise ratio recording. This is now embedded with electrical stimulation for stream out electrical responses also. So in summary, I try to give you an overview of emerging CMOS-based data. Of course, SiNAPS is scaling up the volume of data we are collecting, which is a challenge for pre-processing the data, for spike detection, and also for handling this data among labs. And I think this community is developing a lot of tools for simplify our life in this direction. I try to show you where we are going in terms of developments, and actually our front-end circuits are 28 by 28 microns in size, but they can be even scaled down. And this is actually providing new tools for neuroscience research, but also for brain-machine interfaces with unmatched bandwidth. And I think one of the value of having so many channels is to be able to adapt basically over time, because this, as we show in previous paper in vitro, you can basically drive the selection of informative neurons over time. So you don't need necessarily to stream out all this data over time, but you can basically select over time. And this is a concept we are trying to push forward also with Matteo's work. So let me acknowledge funding, the European level, also Brain Initiative supported our development of SiNAPS, and ongoing project funded by the European Innovation Council, CrossBrain, also by the PNRR project in Italy, supported by the European Union, RAISE, and of course, Corticales team and Plexon, NeuroNexus for giving the chance to bring all this into the labs of many researchers. Thank you so much. This is a view from Genova. You are more than welcome to join us also. We change a little bit from Edinburgh. Thank you. Yes, please.
I'm curious about photo artifacts.
Yes.
That you might see on probe.
Yes.
Do you have an idea of what like the
Yeah, absolutely. So I didn't report this part. I have a postdoc working only on this. And of course, you have photo artifacts, but we also build up technology to avoid these artifacts, basically introducing layers that are protecting the underneath circuit. I agree that this might be due to switching circuit at the local site, but the current devices are able to stand photo stimulation. And we are integrating probes that combine tapered optical fibers. You might know the work done by colleagues in Lecce and IIT with Bernardo Sabatini in Harvard. And we are integrating these two devices, which allows us basically to select the light emission sites, the position, and record single units. Yeah. So this is ongoing, and there is a paper coming out soon on that topic too. Yeah. You're welcome. Yeah, that's really good point. Something else we have been doing, combining optogenetic, is optogenetically stimulate one brain area and look into the recording on the other side. And that was mainly due to study the connectivity among these two circuits. This is another work that is actually ongoing with Raffaella Tonini at IIT. Everything clear, fantastic. I did well my job.
Question? All right, good. Thank you again, Luca.
Thank you to you. Thank you.
So we've got next up at lunch. I'm actually not entirely sure if they are ready, but it'll be in the cafe area sooner or later. We'll be back in here at 1:45.